Okay. So let me just recall the setup. We have a precompact domain D with smooth boundary in our Riemannian manifold. And we have a function f. Let me, for simplicity, say it's smooth and boundary D. And then let me just call this space C. So this is the set of U in, well, so C infinity D closure, let's say. Such that U restricted to boundary D is equal to F. Okay. So this space, what is the structure of this space? This is equal to an affine subspace of the space of functions, right? This is, if I take one function here, U naught, then I can add any function whose boundary value is 0. So functions whose boundary value is 0, that's a vector space, right? So this is U naught plus some vector space. Let me call this V, okay? Where U naught belongs to C and V is the vector space of functions whose boundary value is 0. So this is a vector space. Now on this affine space, I have an energy function. E U maps to the integral over D of norm grad U squared d4.
Half.
So half, yeah, thanks. Okay, so I want to compute the derivative of this function, right? So this is it's an affine space. So at any point you can think informally, you can identify at any point the tangent space to C. You can identify it with the vector space V itself, right?
Right.
Yes. Okay.
Yes.
Okay. So now I want to, so let's take a U in C. And I want to compute the derivative of this energy function at the point U. So this is going to be a linear function from the tangent space to C, which I identify with the vector space V to R, right? So if I take a little v in V, then I can say that what is a d derivative of the energy function applied to little v. This is going to be ddt at t equal to 0 of E of ut, where now here ut is any curve. So let me take a u naught here, u naught. So where ut, this is just defined for t small, for mod t less than epsilon. is any curve in C
Right.
any smooth curve such that ddt at t equal to 0 of ut is equal to v. Okay. Yeah.
Okay.
So now this derivative we found, this is equal to minus the integral over d of v, sorry, no inner product, just v times Laplacian u, Laplacian u naught. Sorry. Right, this is the computation we did.
Mm.
Now, the thing is, this since the tangent space at each point, I mean, this is an affine space, the tangent space at each point is this vector space. The vector space is a subspace of the space of smooth functions. So, well, it's not a Banach space, it's a Fréchet space. But we can still put an inner product on it, the L2 inner product, right? So we have the L2 inner product on V, which is the inner product of V1, V2. Is just the integral. Yeah, so, okay, fine, yeah. So the integral over d, V1, V2, that's all, V1, V2. The usual L2 inner product default. So then this derivative of the energy function acting on V, this I can write as minus the L2 inner product of Laplacian u naught with V.
Right.
Now recall what is the definition of gradient on a Riemannian manifold. Grad f, grad of a function, say g, is defined by the equality dg acting at a point, say P, acting on V, is a vector, inner product of a vector grad G at P with V, right? I mean, this dg is a linear functional. So, and on an inner product space in finite dimensions, it's just given by inner product with a vector, right? So that vector is defined to be the gradient vector. So in this case, what we're seeing is this is inner product with minus the Laplacian. So in that sense, the gradient of E at the point u naught, this is equal to minus the Laplacian.
Right.
So that's all. So so what is the gradient flow of minus the energy function? This is going to be an ODE on the space C. So an ODE on the space C means we have a curve UT in the space C. And then we want that ddt of ut is equal to mi minus grad E of ut. And minus grad E of ut, this is equal to Laplacian ut. So the gradient flow, this ODE on the space C, this becomes just the heat equation. This becomes the heat equation. So the integral curves of the gradient flow of minus the energy, those are solutions of the heat equation. Right? So integral curves of minus grad E equal to solutions ut of heat equation. Is this clear now? So, is this all right, Rudhana?
Yeah. Yeah, I think so. Yeah, I'll read it again. I mean,
So, I
something
mean,
is bothering me.
see this computation with the curve ut here, this is any arbitrary curve whose tangent vector is equal to v. That's all. It's just a curve whose tangent vector is equal to v.
Right.
Then you do this computation, you get this derivative is equal to minus this integral. Yeah. And so this is true for any v,
Equal
right?
to?
Minus this integral, v times
Achha.
Laplacian,
Okay.
right? Now this is true for any tangent vector v, right? So we've completely computed the derivative of the energy functional. That's a linear map from v to r. Right?
Okay.
So we've computed this linear function. This is the inner product of v with minus Laplacian u naught. So that means that, I mean, see, where this is heuristic in the sense we are not working in finite dimensions, we're working in a Fréchet space. So, I mean, you have to be a bit careful. We're not working in the Riemannian setting, really. So this is a, in a sense, it's just a, I mean, in order to define a gradient vector field, and see, for Riesz representation, you need a Hilbert space, right? You need completeness. So with this L2 inner product, this space of smooth functions is of course not going to be complete, right? You would have to take its completion. So we're not doing all that. That can be done. I think people have done that, but we're not doing that. This is just a heuristic motivation for that the gradient vector field should be minus the Laplace. So if we continue with this picture, then we can answer also a question, Orkojit's question, that if you take a harmonic function with the correct boundary values, then is it the minimizer of the energy? So that we can actually answer by computing the second derivative of the energy. So along straight lines. So since our space is an affine space, we can look at straight lines in our space, right? So let's look at the second derivative of the energy. So the picture is like this. Here's say U naught, and then any other point U, right? You can join by a straight line in this space, right? Since it's an affine space, right? This vector U minus U naught belongs to V, right? The vector space V, right? So,
Right.
so if we look at this line segment, then the energy function becomes just a function of one variable on this line segment. Let's look at its second derivative along this, right? So, so suppose I take U naught and U in V, and then I say, sorry, in C. So then I let well, say U naught and U1, okay, and I let V be U1 minus U naught. This is in my vector space capital V. So then I look at the curve UT. This is the straight line segment. It's U naught plus TV. T belongs to 0, 1. Okay. So this joins the 2 points U naught and U1, right? Okay. So let's look at, so we know what the derivative of the energy function is, the first derivative. So ddt of energy of UT, this is minus integral. So basically ddt of UT Laplacian UT, right? Okay. So this is going to be minus integral of V Laplacian UT. Because ddt of UT is constant equal to V, right? It's a straight line. So the derivative is constant equal to V. And so now we can calculate the second derivative. So d squared dt squared of E of UT. This is going to be so ddt of minus this integral V Laplacian UT. And that is I can differentiate under the integral sign, right? So when I differentiate, I'll get Laplacian of d dt ut. So that is V, right? So that's Laplacian V. So this will become minus integral over d of V Laplacian V dvol, right? Yes? Okay. Is this correct? Right? Yeah. And then this integral we already know how to do, right? This we can, because V vanishes on boundary D, when you do an integration by parts, this is going using the formula for divergence of phi x, where phi is a function and x is a vector field. This integral we already computed. This is going to be the integral over D of norm grad V squared, right? Yes?
Yes.
Okay. So this is, what does this tell us? This is greater than or equal to 0, therefore. In other words, this second derivative is greater than or equal to 0. That means this function is convex, right? This E of ut along this straight line. So restricted to straight lines, the energy function is convex, right? So therefore, E is convex, restricted to straight lines in C. Okay. Now, suppose U naught, the starting point of this straight line, is a harmonic function. Okay. So now suppose U naught is harmonic. So then if we let phi of t be the function of one variable, which is E of ut. Okay. Then we know that phi double prime t is greater than or equal to 0 for all t. This we've just computed. And phi prime 0, that's the derivative of the energy at t equal to 0. This is equal to minus integral v Laplacian u naught. So if we assume that u naught is harmonic, then this is 0. So this phi prime 0 becomes 0, and phi double prime is greater than or equal to 0. So that implies, so phi prime is monotone increasing, and its value at 0 is 0. So that implies that phi prime t is greater than or equal to 0 for all t. And that implies that phi of 1 is greater than or equal to phi of 0. And phi of 1 is the energy of u1, and phi of 0 is the energy of u naught. So therefore, u naught has minimum energy. Is this clear, Orkojit?
Yes, sir. Yes, yes.
Okay. So
So
what
I
is the,
take any other function and just look at the double derivative along the state.
yeah, so if you do this, what is the picture of the energy function that you're getting? If you draw the graph of the energy function, it's going to be convex along all of these. This is going to be a minimum, a global minimum, right? And the graph is going to look something like this, like the graph is going to look something like this, right? This is what the graph of the energy function will look like.
Right.
You see? Okay, and these
Yes.
curves will be these will be the gradient curves. This is the graph of the energy function.
You had
And
drawn
this,
this picture yesterday also, last day also.
there I didn't draw the graph. I didn't draw the
Yeah.
graph. I was drawing the space C. But
Yes.
the space C is an affine space. It's just a constant. It's just a translate of a vector space. So the space C is a vector space essentially up to a constant, and then this is the graph of the energy function on space. Is this picture clear?
Yes, sir. Fine.
Rudroda, is this all right?
Yeah. It's already here.
No, it's okay. So that proves that the harmonic function is the solution of the Dirichlet problem is the minimum energy function. Okay, so now Utsav, is this okay?
Yes, sir.
Yeah, it's okay. Yeah. Okay, so now let's come back to what we started talking about last time, which was elliptic operators in Rn. So an elliptic operator on a domain D, second order elliptic operator had this form, summation Aij del squared f del xi del xj, a second order term plus a first order term summation bi del f del xi plus a zeroth order term c times f, where Aij, bi, and c are continuous functions on the domain D. And elliptic means that the lowest eigenvalue of the coefficient matrix Aij at each point is it's uniformly bounded below by a positive constant lambda. So the Laplacian, of course, is an example of an elliptic operator, the Euclidean Laplacian. And more generally, if we take the Laplacian on a Riemannian manifold, if we take it in a coordinate chart and embed the chart into Rn, then in that chart in coordinates, we saw that the coefficient matrix of the Laplacian is the inverse of the matrix of the Riemannian metric, right? It was G upper Ij. So on a compact domain, that G upper Ij, the lowest eigenvalue by compactness will be bounded below, right? So the Laplacian will be elliptic on compact domains in my Riemannian manifold. Okay. So we want to study the Dirichlet problem for the operator L, right? So just 1 second. So that means given a function f, well, we want to study it really for the Poisson equation, the inhomogeneous Laplace equation. So for the operator L, so given f a continuous function on the domain D and phi a continuous function on the boundary of the domain D, find u, which is C2 in the interior and continuous on the closure, such that Lu is equal to f in D and u is equal to phi on boundary D. Okay. So we are going to describe a solution to this problem for the unit ball. Okay, so for the unit ball, we've already solved this problem when L is equal to the Euclidean Laplacian, right? And f is bounded and locally Holder continuous. Those were the assumptions we needed, right? Then we've solved this problem for the Euclidean Laplacian. Now the idea is to consider any elliptic operator L and consider it as a perturbation of the Euclidean Laplacian by defining the family, one parameter family of operators. LT is just a convex combination of L0 and L, okay, where L0 is the Euclidean Laplacian. So you take 1 minus T L0 plus T times L, okay. And the idea is now to use what's called the method of continuity, which is abstractly the following functional analysis result. It says the following. Okay, this is the method of continuity. So let E and F be Banach spaces and let L0 and L1 be bounded linear maps from E to F. Okay. So then you take the convex combination of this L0 and L1, call it LT. So this is 1 minus TL0 plus TL1. Okay. Now suppose that there is a constant C such that norm of U is less than or equal to C times norm of LTU for all U in E and for all T in 0, 1. Okay. All right. So if, so what does this imply, this inequality? First of all, this implies that LTs are all 1 to 1, right? If LTU is 0, then of course U will become 0, right? By this inequality. So the LTs are all 1 to 1. And if they were onto, then what does this say? This would say that the norm of LT inverse is bounded by 1 over C, right?
Right.
Yes.
Yes.
Right. It would. The
Right.
norm of LT inverse is bounded by 1 over C. Okay. So that's what this inequality is saying, essentially, that the norms of the inverse operators are uniformly bounded by a fixed constant 1 over C. So anyway, now what the proposition says is that L1 is onto if L0 is onto. Okay. So if the initial operator is onto, then the final operator is also onto. Okay. So the proof is a connectedness argument. So let A be the set of T in 0, 1 such that LT is onto. So we're assuming that L0 is onto. So this set A is non-empty. 0 belongs to this set. Okay. So now let delta be this constant, half into 1 over C into 1 over norm L0 plus norm L1. Okay, so this is some positive constant. Okay. All right. So now suppose, so what we want to show is that this set A is open and closed, right? It's all, we're already assuming it's non-empty. So then it will be all of the interval 0, 1 by connectedness. And so 1 will belong to this set, and that means that L1 will be onto. Okay. So we have to show this set A is open and closed. So first we'll show that this set A is open. Okay. So suppose some T belongs to A, that means LT is onto. Okay. Then we want to show that for S close to T, LS is also onto. Okay. So as we've already observed, the given inequality here implies that LT is 1 to 1. So if we're also assuming that it's onto, then it has an inverse, LT inverse. And as we've said, the norm of LT inverse, there's a typo here. This should be 1 over C. This is less than or equal to 1 over C. Okay. No, sorry. No. It's not 1 over C. It's C. It's no. This is correct. I'm sorry. No. The norm is less than or equal to C. Yeah. I mean, you put U equal to LT inverse of V, and then this U becomes norm of LT inverse V is less than or equal to C times norm V. No, I was wrong, sorry, earlier. The norm of LT inverse is bounded by C, not 1 over C. It's bounded by C. Yeah, okay. All right, now let epsilon be in the interval minus delta to delta. And let S be T plus epsilon, okay? And well, choose epsilon such that this belongs to the interval 0, 1. So I'm just looking at the interval T minus delta to T plus delta, and I'm taking its intersection with the interval 0, 1, and I'm taking a point S in that intersection. Okay. Now, given an element little f in the Banach space capital F, right? What we want is to show that there exists a U such that LS of U is equal to F, right? We want to show that LS is onto. Yeah. So we want to solve this equation. Now the idea is to use the contraction mapping principle and show that a solution of this equation is a fixed point of a certain contraction, of a contraction operator. All right. So what we do is we rearrange this equation. So S is equal to T plus epsilon. So LS is going to, I can write this as LT plus epsilon L1 minus L0, right? So this becomes LTU plus epsilon L1 minus L0U equal to F. Now I rearrange, I want to write it as a fixed point equation. So what I do is I solve for U. So because LT is invertible, I can multiply by LT inverse everywhere. And then I can keep U on this side and take the other terms to the right-hand side. So then this is equivalent to U is equal to LT inverse F minus epsilon LT inverse L1 minus L0 U, right? So this right-hand side I think of as an operator from E to E, right? This is going from E to E. So let me call this P sub F, right? So P sub F is the operator from E to E. P sub F of U is LT inverse F minus epsilon LT inverse L1 minus L0 of U. Okay. So all we have to do is show that this is a contraction. So we look at okay. So we defined this operator. We've written this equation LSU equal to F as a fixed point equation, U equal to P sub F of U, where P sub F is a operator from the Banach space E to itself. P sub F of U is LT inverse F minus epsilon LT inverse L1 minus L0 U. So look at P sub F U minus P sub F V. So then this LT inverse F, this is constant. This will cancel from both these terms. And so what you'll get is epsilon. When you take norms, then you'll get mod epsilon into norm of LT inverse L1 minus L0 norm into norm U minus V, right? And this is less than or equal to norm LT inverse into norm L1 minus L0. And by hypothesis, norm of LT inverse is less than this constant C. And mod epsilon is less than delta, right? So we get delta into C into norm L0 plus norm L1, right? Okay. And so by our choice of delta, this constant is less than a half. Okay, so the whole thing becomes less than half times norm U minus V. That means that this operator PF is a contraction. Therefore, it has a unique fixed point U. And that fixed point will satisfy LS of U equal to F. Okay, so that means that LS is onto for all S in the interval T minus delta to T plus delta intersect 0, 1. Therefore, A is open in 0, 1, right? And to show that it's closed, suppose T naught is a point in the closure of A, we have to show that T naught belongs to A. So since it's in the closure of A, that means we can choose an element T in A, which is at distance less than delta from T naught, right? So that means that T naught will belong to T minus delta to T plus delta intersect 0, 1. But if T belongs to A, then we know that this interval intersect 0, 1 also belongs to A. So therefore T naught will belong to A, right? So therefore A is closed, all right? So once we know that L naught is onto, then A is non-empty, open, closed. So therefore it's all of 0, 1. So in particular, 1 belongs to A. That means that L1 is onto. Okay. Is this all right?
Yes, sir.
So this is our idea. So we are going to apply this proposition where L naught is going to be the Euclidean Laplacian and L1 is going to be our given elliptic operator L. That's the idea. Okay. So what we want, the important point is to define the correct Banach spaces where the Laplacian is going to become a bounded operator, right? So your normal spaces may not work, right? I mean, you have to be careful what spaces to choose, all right? I mean, for example, L2 spaces are not going to work at all, right? Because there the Laplacian is not even defined everywhere. It's only densely defined, and even then it's an unbounded operator, right? In the usual L2 spaces, it's an unbounded, densely defined operator. So those are L2 spaces are not the right spaces. So it turns out the right kind of Banach spaces to look at are what are called the Holder spaces. Okay. So now we're going to define the Holder spaces. And there the Laplacian will become a bounded operator between appropriate Holder spaces. So how do we define the Holder spaces? So first, let's define the CK spaces, right? So if D is a bounded domain in Rn, and then recall that the CK norms on D are defined as follows. So the CK norm of D closure is the sum J goes from 0 to K, the sum over multi-indices beta of norm J, and then the sup norm over X in D of the absolute value of the partial derivative d beta u. Okay. So this notation means the usual thing that beta here is a multi-index I1 up to IN, and mod beta is the sum I1 plus IN, and d beta u means del mod beta u del x1 power I1 del xn power IN. Okay, this partial derivative. So mod beta is the order of this partial derivative, right? So what we're doing is we're looking at all partial derivatives of order less than or equal to k, and we're taking all of their sup norms over the domain D closure, and then we're adding up all these sup norms. So that gives the CK norm, right? Okay. And so then the Banach space CK of D closure, this is the set of U in CK of D. So that means these are CK functions in the interior of D, such that their CK norm is finite. Okay, so all the supremums of the partial derivatives of order less than or equal to k are finite, and each partial derivative of order less than or equal to k extends continuously to D closure. Okay, so you need this continuous extension in order to get a Banach space. You need this continuous extension. Okay. So then this CK of D closure, this will be a Banach space. Okay. All right. Now, what we want is a slight generalization of these CK spaces. So these are going to be the Holder spaces. Okay. So CK means what? That means the partial derivatives of order up to k are continuous and bounded and extend to the closure, right? What we want is a slightly better control on our functions. We want the kth partial derivatives to be Holder continuous, not just continuous, but Holder continuous. Okay. So, so let alpha be a number, a positive number less than or equal to 1. Then we define what's called a Holder semi-norm. Okay. So the Holder semi-norm bracket alpha, f alpha, colon d, this is the supremum over xy in D, x not equal to y, of mod of fx minus fy divided by norm x minus y power alpha. Okay. So f is Holder in the domain D if and only if this Holder semi-norm is finite, right? Okay. So now we define now a Holder norm. So notice this semi-norm is not a norm, right? If the semi-norm is 0, it just means that, well, f is constant, but f doesn't have to be 0, right? So it's not a norm, it's a semi-norm. Okay. But we can define a genuine norm, a Holder norm, the CK alpha norm. So we define this on CKD by saying the CK alpha norm is the CK norm of U plus the sup over all indices of length k, multi-indexes of length k, of the Holder semi-norm of the partial derivatives d beta u. All right. So you take all the kth order partial derivatives, take their Holder semi-norms, and take the maximum of them. Okay. And then add that to the CK norm. Okay. And so then the Holder space CK alpha of D closure, these are the functions in CK D closure whose CK alpha norm is finite. Okay. Okay, so it's basically the CK functions on D closure whose kth partial derivatives are all alpha Holder. Okay. All right. Yeah. So that's the extra condition that we need. So for us, when we're studying second order operators, the natural Holder space to look at will be C2 alpha, C2 alpha. So that means you need two derivatives in order to apply your elliptic second order operator. You need two derivatives, but we also want the second derivatives to be Holder continuous. Okay, so the right spaces to look at for us will be C2 alpha spaces. Okay. So this CK alpha space, this is a Banach space. It's not hard to show that. So now let's come back to our elliptic second order operator L. And we make the following assumptions on it. That as before, we have the ellipticity assumption, summation Aij x Vi Vj greater than or equal to lambda norm V squared for all x in D and for all V vector in Rn for a fixed constant lambda positive. Okay. And secondly, now we are going to make some assumptions on the coefficients of our operator L. So earlier we were just assuming continuous. Now we're going to assume that these are Holder continuous. Okay. So, and we take a constant big lambda, capital lambda, which is greater than or equal to the alpha Holder norms of all the coefficients of all the Aij's, Bi's, and the C. Okay. For some fixed alpha in between 0 and.
So our operator is uniformly elliptic.
Yeah, that's the first assumption. That's the uniform ellipticity.
Yeah.
The first assumption. Yeah. The second assumption is that the coefficients are Holder continuous. Okay.
Yes, yes.
For a fixed alpha, right? All the coefficients are Holder continuous. So this will be true if, for example, the coefficients are smooth. Then they'll be Holder continuous. All right.
Yes, yes.
Okay. If the coefficients are smooth, then they'll be Holder continuous. Or even just C1. If the coefficients are C1, they'll be Holder continuous. Yeah. C1 on a domain, well, the boundary of the domain is important. If it's C1 on a smooth domain with smooth boundary, then they will be Holder continuous. You have to be a bit careful about domains with spikes. There, even if it's C1, it may not be Holder. Or may not be Lipschitz, may not be Holder. So, yeah. So you don't want domains with cusps, basically. So if you have smooth domains, I mean, the boundary is smooth, then C1 will imply
On,
Lipschitz.
on nice smooth domains, we have all the nice containments of the Holder spaces, right?
Right. Yeah.
I mean,
That's right.
yeah. Right.
So C1 will be contained in C alpha for all alpha less than or equal to 1. C1 will be contained in C alpha for all alpha less than or equal to 1 on a smooth domain. But that's not true if the domain is not smooth.
Okay.
Okay, if the domain is not smooth, C1 may not be contained in C alpha. Yeah.
And by smoothness, you mean the smoothness of the boundary, right?
Yeah. Smooth means smoothness of the boundary. Yeah. So, I mean, the sort of bad domains, see, what are the bad domains? Bad domains will be something with a cusp, like you take a domain like this. Okay. Then even if it's C1, yeah, or well, let me think for a second. I think this should be the problem, or okay, well, I can cook up a bad domain. Let me cook up a different bad domain. You take let's say you take an open square and you subtract let's say intervals converging to the left hand side. All right, you subtract a sequence of intervals. So that's a closed set. This sequence of intervals union this right hand interval, it's a closed set, right? Because they're converging and I've got the limit here. So when I remove this closed set, I'll get an open set, right? So I'll get a domain. Yeah. Okay.
Yes, yes.
But now, if I want to estimate, let's say the difference between fx and fy, when they are in two parts like this, how do I estimate? Normally, fx minus fy, I write as what? I write as integral of over some curve joining them, right? Of df of gamma t. Yeah, from A to B, right? Where gamma is a curve joining the points x, y. But here gamma will, to join them, this space will not be what's called locally connected. It will not be locally connected. So the point is that you'll have to go out a long way and come back to join these two, right? So if I want an estimate, then the lengths of these gammas are going to go to infinity. So then you can cook up a function so that this distance becomes large. Do you understand?
Yes, yes.
Okay, so even though it's C1, this df is bounded. So, I mean, what is the bound you get? The bound you get is that this is less than or equal to the L infinity norm of df into the length of gamma, right? Yes.
Yes.
But the problem is the length is going to infinity. So even if this is bounded, this you can make this very large. Okay. And so then what you're looking at is this norm x minus y power alpha. Okay, so you get this. Okay, so you can make this go to infinity. This length divided by norm x minus y power alpha. You can make this go to infinity. Okay. So yeah, so unless it's smooth, there will be a problem. Yeah. Okay.
Yes, sir.
So yeah. So this is an example where C1 of D closure is not contained in C alpha of D closure. Yeah. Okay. All right. Okay, now the solution of the Dirichlet problem for the equation LU equal to F in bounded domains with smooth boundary. So we're only going to work with smooth boundary. So via the method of continuity is based on the following results, which we will cite without proof. Okay. So these are from Gilbag and Trudinger. You can look at that book if you want to, but I mean, the proofs are non-trivial. They take quite a bit of work. So we're not going to do them, but I'm just going to state them. So first, theorem A is a maximum principle. So let D be a bounded domain. Then there exists a constant C, which depends only on the ellipticity constant, lambda, and the Holder norms of the coefficients, so capital lambda and the domain D, such that the following holds. So yeah, so these maximum principles, the one hypothesis that we always need for the maximum principle is that the zeroth order term C of the operator L is always less than or equal to 0. Okay. The zeroth order term you always need less than or equal to 0. So the maximum principle says if F is a continuous function on D closure and U is C2 in D and C0 on D closure, then if LU is greater than or equal to F in the domain D, then the sup of U over D is less than or equal to the sup over boundary D of U plus constant C, this constant C times the sup over D of mod F minus. Okay. Okay. And if LU is equal to F in D, then the sup of mod U over D is less than or equal to the sup of mod U over boundary D plus C times the sup of mod F over D. Okay. So actually, let me just say if this F is equal to 0, that's the case we normally look at, right? And L was the Euclidean Laplacian, then this becomes a subharmonic function. And this is the usual maximum principle. You don't need this U plus in that case. It just works with the U also. The sup of U is less than the sup of U over boundary D. And the second condition is for harmonic functions. If LU is equal to F, where F is 0 and L is the Euclidean Laplacian, then you get a harmonic function, and then the sup of mod U over D is less than or equal to the sup of mod U over boundary D. That's the weak maximum principle for harmonic functions. So, I mean, the point of this estimate is that we're not assuming that LU is 0 or LU is greater than or equal to 0. We have a function F here in the right-hand side. Okay. So this is a more general maximum principle. Right. And that function leads to this extra term here, a constant times the sup of mod F. Okay. Is this all right? Yeah.
Yes, sir.
Okay. So we're not going to prove this, but yeah. And then the main estimates which will allow us to use the Banach spaces, the Holder spaces, is these what's called Schroeder estimates. So here we need a domain with smooth boundary. Okay, so let D be a domain, bounded domain with smooth boundary, and let F be in C alpha of D closure, and let phi be in C2 alpha of D closure. Okay, where alpha is fixed in between 0 and 1. Then there exists a constant C, which only depends on the dimension n, on the exponent alpha, the ellipticity constant lambda, and the Holder norms of the coefficients, capital lambda, and the domain D, such that the following holds. If U is a C2 alpha function on D closure, which is a solution of the Dirichlet problem, the inhomogeneous Dirichlet problem for the operator L, LU is equal to F in D. So this F is alpha holder, and U is equal to phi on boundary D. Okay. Then the C2 alpha norm of U is less than or equal to a constant times this constant C times the C0 norm of U plus the C2 alpha norm of phi plus the C alpha norm of F. Okay. So you see, we're getting an improvement in what is the non-trivial thing here. On the left-hand side, we have all the second order derivatives, right? All the derivatives up to order 2 and their partial derivative, their Holder norms of the second order derivatives, right? The alpha Holder norms of the second order derivatives. On the right-hand side, we only have the 0th order derivative, that means just the function itself, and the only place where the second order derivatives of U come in are in this term F, right, where F is LU. So that means basically from the derivatives occurring in L, right? We get an estimate of all the derivatives. Do you understand? So we're getting an estimate of all the derivatives up to order 2 in terms of only LU, right? In terms of only LU. Okay. So that's the content of this theorem B. Okay. So now from these above two theorems, we can use the method of continuity to prove the following result. Okay. So we're going to assume that the 0th order coefficient of the operator L, little c, is less than or equal to 0, so that the maximum principle holds. Okay. So we have the following theorem. Let D be a bounded domain with smooth boundary. Suppose that the following holds. Okay. That is, the Dirichlet problem for the Laplacian is solvable with good boundary values. So what does that mean? That means for all f in C alpha D closure and phi in C2 alpha D closure, there exists U in C2 alpha D closure such that Laplacian U equal to f in D and U equal to phi on boundary D. Okay. So that means for the Poisson equation, delta U equal to f, we're assuming the f is a globally holder on D closure. So not just locally holder, but globally holder on D closure. And for the boundary values, this U equal to phi on boundary D, what we're assuming is that the boundary function, it extends to a C2 alpha function on D closure, right? That's what we're assuming. The boundary values are nice. They extend to a C2 alpha function on the whole domain. Okay. So suppose that this problem is solvable, all right, for the Euclidean Laplacian, then what we can prove is by the method of continuity, the same problem is going to be solvable for any second order elliptic operator L. Okay. That means for all f in C alpha D closure and phi in C2 alpha D closure, there exists a unique U in C2 alpha D closure such that LU is equal to f on D and U is equal to phi on boundary D. Okay. So this we're going to prove by the method of continuity. Okay. You see, this assumption about the solution of the inhomogeneous Dirichlet problem for the Laplacian, this is telling us that the Laplacian restricted to certain function spaces is going to be onto, right? For every f, we're getting a U which satisfies this, right? So, yeah. Okay. All right. So first we have to see that our operator L and the Laplacian are bounded operators between appropriate holder spaces. So that needs just a little bit of work. So first we cite, again without proof, what are called interpolation inequalities for the holder norms, okay, on bounded domains with smooth boundary. Okay, so Utshab, these are going to give the containment relations between the holder spaces, all right?
Yes, yes.
So suppose JK are non-negative integers and alpha beta are in between 0 and 1. And suppose that J plus beta is strictly less than K plus alpha, okay? Then there exists a constant capital K such that the J beta norm of U is less than or equal to the K times the C0 norm of U plus the K alpha norm of U. Okay. Okay, so that means basically if J plus beta is strictly less than K plus alpha, then if the K alpha norm is finite, then the J beta norm is going to be finite. Right, so the space C J beta is going to be contained in the space C K alpha, right? So that's the containment you're getting. Oh, sorry, the CK alpha is going to be contained in CJ beta. It's the other way around. Yeah. The
Yeah.
higher,
Mhm.
right? CK alpha is going to be contained in CJ beta, right? If this norm is finite, then this norm is also finite.
The higher exponent is included in the smaller exponent.
Lower end.
Yeah.
Right. Yeah. Which makes sense intuitively, right? Yeah. So
Because the
the
higher,
higher,
higher the exponent, the more the control we have. Yeah.
yeah, you have control on more derivatives, right?
Right.
So
Yes.
that should imply, yeah,
Yeah.
control.
Yeah.
But I'm making a remark, like I said earlier, this is only true for domains with smooth boundary. So the smoothness of the boundary is still important. Okay.
Yes. Yes.
It's still important. Okay. All right. Now, so if we apply the interpolation inequality, where J is 1 and K is 2, and beta is equal to alpha, then we get that the C1 alpha norm of any function u is less than or equal to K times the C0 norm plus the C2 alpha norm of u. Okay. Now, from this, what we will get is that when we look at LU and the alpha norm of the C0 alpha norm of LU, this we will be able to show is less than a constant times the C2 alpha norm of U. Okay, now how do we show this? So just look at what is LU. So LU is summation Aij del squared U del xi del xj plus summation bi del u del xi plus cu. Okay. Now, to control, what are we looking at? We're looking at the C0 alpha norm of LU, right? So the Holder norm of this. Okay. So how do we control that? So first of all, we know this Aij's, these are in C alpha, right? Okay. So we have a bound on, so when we're looking at the Holder semi-norm of this product, it's going to be bounded. You have sort of a product rule for the Holder semi-norm. All right. So, so this will be bounded by Holder norm of Aij's. That's bounded by a fixed constant times sup norm of this. So that is bounded by the C2 norm, which is bounded by the C2 alpha norm, right? And similarly, you'll have the Holder semi-norms of these the Holder norms of these, which are bounded by the C2 alpha norm of U, right? So all of this stuff, all of this together, this will be bounded by a constant times the C2 alpha norm of U, right? Is that clear? Yeah.
Yes.
Okay. And now when I look at this BIs, these are in C alpha, and this del X, del U del Xi, this is also going to be in C alpha, because by the interpolation inequalities, I know that the C1 alpha norm is finite, right? So the C1 alpha norm, not only is it finite, the C1 alpha norm is bounded by a constant times the C0 norm plus the C2 alpha norm, right? Okay. So in particular, that means if I look here, the alpha Holder semi-norm of these first derivatives, that's going to be bounded by a constant times the C2 alpha norm, right? And these are bounded by a constant, these C alpha norms of the BIs. So the product again will be, this will also be bounded by, see, this is going to be bounded by a constant times the C1 alpha norm, which will be bounded by a constant times the C2 alpha norm, right? Is this clear? By the interpolation inequalities.
Yes.
Okay. So that's it. And then the last term is just bounded by the C0 norm, right? So this is less than a constant times the C0 norm. And of course, C0 norm is bounded by the C2 alpha norm, right?
Yes.
So all of them are less than constant times C2 alpha norm. So when you add up, you'll get the sum is bounded by constant times C2 alpha norm. Is this okay?
Yes, sir.
Yeah. So what does that mean? That means that if I look at L going from C2 alpha to C alpha, right? Look, if U is in C2 alpha, then we've seen that LU will be in C alpha, right? Because this norm is finite then. And moreover, it's a bounded linear map, right? This inequality just means that L from C2 alpha declosure to C alpha declosure, this is a bounded linear map, right? Okay. So now for the solution of the Dirichlet problem, what we're going to do is first look at a closed subspace of C2 alpha declosure. Those are going to be the U in C2 alpha declosure whose boundary value is 0, right? Okay. So this is a closed subspace of C2 alpha declosure. And so this subspace E is a Banach space. All right. Yes.
Yes.
So now look at the operator L from E going into C alpha declosure and look at the Euclidean Laplacian from E to C alpha declosure. Both are bounded linear maps, right? Now we want to apply the method of continuity. So you let LT be 1 minus T delta plus TL. So LT, what are the second order coefficients? They are T Aij plus 1 minus T delta Ij, right? And then the first order coefficients are T Bi and the zeroth order coefficient is TC. Okay. So if we let lambda naught to be the minimum of 1 and lambda and capital lambda naught to be the maximum of 1 and capital lambda, then the coefficients of LT, what do they satisfy? So let's look at the ellipticity constant for LT. So summation Aij Tx Vi Vj, this is going to be T summation Aij x Vi Vj plus 1 minus T summation delta Ij Vi Vj. So the first term is greater than T lambda norm V squared and this plus 1 minus T norm V squared. And since lambda naught is the minimum of 1 and lambda, this will be greater than or equal to lambda naught norm V squared, right?
Yes, sir.
Okay. So we've got that these LTs are uniformly elliptic for all T with the same constant lambda naught here. Okay. So, all right, let me stop here. We've got less than a minute. We'll start again.
After 1 minute.
Sure, after a couple of minutes. Okay, we'll take a break. One. Yeah, sure. Okay, so what are we getting? We're looking at these operators LT, which are 1 minus T times the Laplacian, Euclidean Laplacian, plus T times the elliptic operator L. So what we find is that what's easy to see is that the ellipticity constant for the operators LT is fixed, independent of T, right? They're all elliptic with ellipticity constant lambda naught, which is the minimum of 1 and lambda. Okay. So 1 is the ellipticity constant for delta, for the Laplacian, and lambda is the ellipticity constant for L. So it's easy to see when you take a convex combination, the ellipticity constant for LT is at least lambda naught, okay, the minimum of 1 and lambda. And similarly, the Holder norms of the coefficients of LT, these are going to be bounded by capital lambda naught, which is the maximum of 1 and capital lambda, right? Okay. All right.
Yes.
Yes.
Okay. So what does this mean? That means that all the operators LT satisfy these two hypotheses with fixed constants, little lambda naught and capital lambda naught, right? So therefore, by the Schroeder estimates that we had, let me recall for you the Schroeder estimate here. The Schroeder estimate was giving you a boundedness here, where this constant C in the inequality, this only depends on the ellipticity constant lambda and the Holder norms of the coefficients, a bound on the Holder norms of the coefficients. So these two are fixed here. For all the operators LT, we have a constant lambda naught and a constant capital lambda naught. So these are fixed. So that means we get a fixed constant C for which this inequality holds, right? For all the operators LT. Okay? Yeah. We get a fixed constant.
Yes, yes.
So that is the point. So now, if I apply the Schroeder estimate, yeah. So let me take a U in C2 alpha D closure, and let me put F to be LT of U, right? And let C1 be the constant from theorem A, which is the maximum principle, and C2 is the constant from theorem B, which is the Schroeder estimate. So now suppose that U is in E, that means the boundary value U is 0 on the boundary of D. Then what do we have? Then we have, by the Schroeder estimate, the C2 alpha norm of U, this is less than or equal to this constant C sub 2 into what? The C0 norm of U plus the C2 alpha norm of the boundary value function. So the boundary value function is 0, and then 0 extends to the function 0 on the whole domain, right? Which is of course a C2 alpha function. That's my function phi in the Schroeder estimate, right? So let me recall for you the Schroeder estimate again. Yeah, here. So we're taking U equal to phi on boundary D, where phi extends to a function on C2 alpha D closure. All right. So if phi is 0 on boundary D, then I can just take the extension to be the 0 function, right? Okay. And then my estimate here, I will have the C2 alpha norm of phi. So that's going to vanish. This term is going to vanish. And then I have the C alpha norm of F. Okay. So I have C2 alpha norm of 0 plus C alpha norm of F. Okay. Now I use the maximum principle theorem A. All right. So what does the maximum principle say? It says that if LU is equal to F, then the C0 norm of U is less than or equal to the C0 norm of U on the boundary plus this constant C times the C0 norm of F, which is LU. Okay. So let me apply this inequality here. So then I'll get the C0 norm of U. This is going to be less than or equal to what? C0 norm on the boundary. So C0 norm on the boundary is 0 plus this constant C1 into C0 norm of LU, which is F, right? Of LTU, which is F. Okay. So these two zeros go away. And finally, what do I get? I get C2 into C1 plus 1 into norm F, C alpha declosure, right? Yes. And F is my LT of U. So this gives me C times norm LTU, C alpha declosure. Is this all right?
Yes.
So what is this? This is exactly the inequality that we had in the method of continuity, right? In that proposition, it's saying that norm U is less than a fixed constant into norm of LTU, right?
Yes.
That's exactly what I needed in the method of continuity. Okay. And now we are assuming by hypothesis that the Dirichlet problem for the Laplacian, the inhomogeneous Dirichlet problem for the Laplacian is solvable, right? So that means the operator delta from the Banach space E to C alpha of declosure, this is onto, right? Therefore, from the method of continuity, it means that the same is true for the operator L. Okay, so L from E to C alpha declosure is also going to be onto. Is this all right?
Yes.
Okay, so what does that mean? That means that given any function f in C alpha declosure, there exists a u in E. So that means a function in C2 alpha declosure, which is 0 on the boundary. So there exists a function which is 0 on the boundary such that LU is equal to F. Okay, so we've solved this problem. For any F in C alpha declosure, there exists U in C2 alpha declosure such that LU is F and U is 0 on boundary D. Okay. Now, what we want to do is solve for general boundary values. So, since we've solved for homogeneous boundary values, then solving for inhomogeneous, you do in the usual way. You given a general boundary value phi, which is a function in C2 alpha declosure, and F is again a function in C alpha declosure, you let V be a solution of the homogeneous problem. So V is in C2 alpha declosure such that LV is equal to F minus L phi. Okay. So this problem we can solve with V equal to 0 on boundary D, right? This problem we can solve, yes? Because F is in C alpha declosure. And since phi is in C2 alpha declosure, that means that L phi will be also in C alpha declosure, right?
Yes.
Yes.
Reduces to the previous case.
Yeah, we're just reducing to the previous case. So we get this solution V. Then all you do is you put U equal to V plus phi. So this will be in C2 alpha declosure, right? So then U satisfies. LU will be what? It will be LV plus L phi. And LV is F minus L phi. So plus L phi, though that will cancel to give you just F. So LU will be equal to F like we wanted. And on the boundary, U is also equal to V plus phi. On the boundary, V is 0. So that means U is equal to phi on the boundary. Is this clear?
Yes.
Okay. So this solves the problem. So here you can see where we needed the boundary values to be in C2 alpha declosure, that we need the boundary values to extend to a C2 alpha function inside, right? So that we can do this last step where we construct the function, the solution V, and from that we construct the solution U, right? Okay.
Yes. So, sir, can you repeat this last thing what you said?
Yeah, here in the last step, you see that we need the function, the boundary values phi to extend to a C2 alpha function inside, right? So
okay,
that we
so
can.
This is the only place where we require this.
Yeah, we didn't need it in the earlier step. In the earlier step, we don't need anything because earlier step, the boundary values are 0. So there's,
Right.
it's just a fixed 0 is the only boundary value there. right? But for general boundary values, if you want to do this last step, you need phi to be in C2 alpha, right? Declosure. Okay. Yeah, because we want to take LV to be F minus
Yes.
L phi, right?
Right.
So this F minus L phi, if we want to solve LV equal to this, we need this F minus L phi to be in C alpha, right? So that means that L phi should be in C alpha, right? That means phi should be in C2 alpha, right?
Right. Yes.
Okay. So to do this, we need phi to be in C2 alpha. And then if we want the solution U to be V plus phi, we want this to be in C2 alpha, then we want phi also to be in C2 alpha, right? Because V is in C2 alpha. So the sum, for the sum to be in C2 alpha, we need phi also to be in C2 alpha, right? Yes.
Yes.
Right? So that's where we need that. And so for last remark is that the uniqueness of this solution U to this inhomogeneous Dirichlet problem, that follows from the maximum principle, right?
Yes.
Because
Yes.
I have two functions, LU1 equal to F and LU2 equal to F, then L of U1 minus U2 is equal to 0, right? And when LU is equal to 0, then I have, and also the boundary values of U1 minus U2, that will be phi minus phi, that will be 0 also. So then this, this maximum principle here, part B, the sup of mod U is less than sup of mod U over the boundary plus C times sup mod F. Here, this F is going to become 0. So this second term will vanish. And this sup over the boundary is 0, so therefore U is 0. Okay.
Yes.
Okay, so that gives the uniqueness of this solution as well. Okay, so we've got existence and uniqueness of a solution where the problem is basically two conditions. One condition is the value of L inside the domain. LU is equal to F in the domain. So this is like the Poisson equation. And then what is the Dirichlet part is the boundary values, right? U is equal to a given function phi on the boundary. Where this function phi is, we are assuming is C2 alpha. Okay. We will remove the condition C2 alpha for the boundary values, but that will take some work. We're going to show that actually we can get the solution also when phi is just C0 on the boundary. Okay, but that will take an approximation argument. We'll do that later. Okay, so up to here, is this okay?
Yes, sir.
Yes.
Yeah. Okay. All right, now, so basically we've reduced a solution of the Dirichlet problem for L to solution of the Dirichlet problem for the Laplacian delta, right? Via the method of continuity. That is the gist of what we've done so far, right? Yeah. So for the solution of the Dirichlet problem, we described already, if you remember last class, we described the solution of the Dirichlet problem for the Euclidean Laplacian, right? Yeah, we did that last time. So,
Yes.
yeah, this was the theorem. Dirichlet problem for Poisson's equation on the unit ball. We did this just for the unit ball, right? So here we took F to be locally Holder continuous and bounded on the unit ball, and phi was in fact just continuous on the boundary. Then we got that there is a unique U which is C2 in the ball and C0 on the closure, such that Laplacian U is F in the ball and U is phi on the boundary. Okay. And so we've already done this. Okay. So all we need to say now is that in order to apply the last theorem that we just proved, we want to say that if phi extends to a C2 alpha function on the ball, then this solution U is also C2 alpha. Okay. So see, the solution is C2 already, right? The solution is C2. We just need to say that if the boundary values extend to a C2 alpha function, then the solution is going to be C2 alpha, right? Is that clear? Yeah. Okay. So that is a theorem which is proved in Gilbert and Trudinger. We're not going to prove that. Oh, sorry. Okay. Right. So, yeah. So actually what they prove is the following. So suppose U is in C2 of the ball and C0 on the closure. And suppose F is alpha holder on the whole ball. So not just locally holder continuous, but globally holder continuous. Okay. And suppose Laplacian U is F and U is 0 on the boundary of the ball. Okay. Then U is in C2 alpha of the closed ball. Okay. Okay, so we're going to assume this theorem. And assuming this, we can now give a solution to the Dirichlet problem for any elliptic operator on the unit ball. So the Dirichlet problem will be LU equal to F in the ball B and U equal to phi on the boundary of the ball B. Okay. So now we can prove the following. So let L be an elliptic second order operator where the zeroth order coefficient is less than or equal to 0. And then for any, so this is on the unit ball. Okay, we're just doing this for the unit ball, not for a general domain, just for the unit ball. So then for any F in C alpha of the closed ball and phi in C2 alpha of the closed ball, there exists a unique U in C2 alpha of the closed ball such that LU is F in B and U is phi on boundary B. Okay. So by the previous theorem, we know that, if this problem has a solution for the Euclidean Laplacian, then it will also have a solution for the operator L, right? That's what we proved by the method of continuity.
Yes.
If you have a solution for the Euclidean Laplacian, then you will have a solution for the operator L. So all we have to do to prove this theorem is to show that you have a solution for the Euclidean Laplacian. Okay. So what do we want? We want delta U equal to F and U equal to phi on boundary B, right? So given F in C alpha B closure and phi in C2 alpha B closure, we have to show there exists U in C2 alpha B closure such that delta U is F in B and U is phi on boundary B. Okay. All right. Now, what do we know? We know that from the solution to the Dirichlet problem for the Poisson equation in the ball, there exists a U which is in C2B intersect C0B closure such that delta U is F and U is phi on boundary B. Okay. So this we've already proved, right? What remains to show? What remains to show is that if phi is in C2 alpha B closure, then U is also in C2 alpha B closure, right? If the boundary values are good, then the function U is also good, right? Yes?
Yes.
Okay, that's what remains to show now. So we're going to deduce that from this previous theorem, which I've stated without proof, this theorem C. Theorem C says that if the boundary values are 0, then U is C2 alpha, right? Okay. If the boundary values are 0, then U is C2 alpha on the closed ball. Okay. So somehow we have to reduce C2 alpha boundary values to the 0 boundary value, right? And that we do by the usual way. We reduce things to the homogeneous case, right? So what do? We take V to be U minus phi, right? So then the boundary value of V is going to be 0, right? So we're reducing to the 0 boundary value case, all right? And we let F tilde to be F minus Laplacian phi. So this is in C alpha B closure because phi is in C2 alpha B closure. So Laplacian phi is in C alpha, okay? So then what is the Laplacian of V? It's going to be equal to F tilde, right? Because Laplacian is V is going to be Laplacian U minus Laplacian phi. That's going to be F minus Laplacian phi, which is F tilde, okay? And V is 0 on the boundary B. So therefore, we know that for the function V is in C2 alpha B closure, right? By the previous theorem. If the boundary value is 0 and the Laplacian of U is equal to F, which is C alpha, then U is in C2 alpha. So applying that here, we get that V is in C2 alpha B closure, right? And then we're done because U is equal to V plus phi, right? So V is in C2 alpha and phi is in C2 alpha. So the sum is in C2 alpha, and so we're done. Is this okay?
Yes.
Yes. All right. Yeah, so what have we proved? We have proved that the following theorem: if you have an elliptic second order operator on the unit ball, where the 0th order coefficient is less than or equal to 0, this we need basically to apply the maximum principle, right? Which is used in some of the norm estimates and also in the uniqueness. We need this C less than or equal to 0 for that. Then for any F which is C alpha on the closed ball and phi which is C2 alpha on the closed ball, there is a unique C2 alpha function U such that LU is F in the ball and U is phi on the boundary of the ball. Okay. Okay. So now the last step is to reduce to the situation where phi, we just want to be a continuous function on the boundary of the ball. We will not assume any C2 alpha extension to the closed ball. All right. Here, so far, we've been looking at good boundary values. We're looking at boundary values of functions which are C2 alpha inside, right? So there's some regularity on the boundary value. All right. But the last step is to go to arbitrary boundary values, which are just continuous functions on the boundary. And that we will do by an approximation argument. Okay. All right, so now we've got, by the previous theorem, a solution to the Dirichlet problem, LU equal to F, when F is C alpha, and the boundary values are sufficiently smooth. Namely, the function phi on the boundary extends to a function phi in C2 alpha of the domain, right? Now, for general continuous boundary values, which are only assumed to be in C0 of boundary D, we can also solve the Dirichlet problem for L via an approximation argument. So what we're going to do is approximate phi. This is just a continuous function on boundary D. You can approximate it by smooth functions on boundary D. And then the smooth functions on boundary D, those extend to smooth functions inside, right? So, so the phi we can approximate by functions phi n, which are in C2 alpha. Okay. And then you take the solutions for the problem with the C2 alpha boundary value, phi n, and you call that solution un. And then you have to show that the UNs converge as n tends to infinity to the solution with boundary value phi. Okay, that's the idea. All right. Okay. So we're going to do this approximation argument. So for that, we need some equicontinuity of solutions to the Dirichlet problem, right? So in order to get convergence, we need some equicontinuity to apply Arzelà-Ascoli. So for that, we'll need the following, what are called interior Schroeder estimate. Okay. So you see, the earlier Schroeder estimate actually, where is it? Yeah, here. This earlier Schroeder estimate is for the C2 alpha norm on the closure of the domain, right? So up to the boundary. Okay, so this is an estimate which is valid up to the boundary. Okay, but you also have estimates for functions which are not, which may blow up near the boundary. You have estimates on compact subsets of the domain. So those are called interior Schroeder estimates. Okay, so let me come to this interior Schroeder estimate. So here, our functions may not extend up to the boundary, all right? They're just defined in the interior. Okay, so let L be elliptic, second order, on a domain D, such that the coefficients of L are locally. So now we're just assuming the coefficients are also locally Holder continuous. The coefficients may not extend to the boundary. And suppose U is in C2 alpha of D. So not D closure, just D. All right, so that means it's Holder in the domain D, but not necessarily up to the boundary. Okay. So suppose it's bounded in D. And this C2 alpha D actually means locally C2 alpha in the domain D. All right, it means locally C2 alpha in the domain D. So suppose it's bounded in D and satisfies LU equal to F in D, where F is again locally Holder continuous. Okay. So then for any domain U in D such that U closure is compact and contained in D, we have a constant C such that we get an estimate similar to the global Schroeder estimate. That is the C2 alpha norm on U closure. So because my U is locally C2 alpha, it is C2 alpha on any compact subset of the domain, all right? On any compact subdomain of D, it is C2 alpha. So this is finite anyway. This is less than C times the L infinity norm on D. We're assuming U is bounded in D, plus the C alpha norm of F on U closure. Okay, here LU is equal to F. Okay, so this constant depends on the subdomain U. As the subdomain grows and becomes all of the domain, this constant could go to infinity. All right. So is this statement clear?
Yeah.
So this is local on compacts in the domain. On any compact in the domain, you're getting a Schroeder estimate. All right. The C2 alpha norm of U is bounded by the L infinity norm of U plus the C alpha norm of LU. Okay. Okay. So as a corollary of the interior Schroeder estimates, we get the following. So let L be as above, again, second order elliptic, and let UN be a sequence of C2 alpha functions in D, which are L harmonic, all right? So LUN is 0 for all n. Then if UN converges to U uniformly on compacts in D, then the limit function U is also in C2 alpha of D, and LU is equal to 0. Okay. So this is like the theorem that, you know, if you have a sequence of harmonic functions which converge uniformly on compacts, then the limit function is harmonic, right?
Montel's theorem, yeah.
Well, I don't know if that's called Montel's theorem exactly, but anyway, that's a standard theorem, right? So, yeah, okay. So this is just saying that harmonic functions are closed under uniform convergence, right? Similar to how holomorphic functions are closed under uniform convergence, right? So, I mean, see, what's not obvious is that the limit function is going to be even differentiable, right? Because, I mean, differentiable functions are not closed under uniform convergence, right? Uniform limit of differentiable functions is not necessarily differentiable, right? So here the point is the stronger condition of this L harmonic implies the limit is C2 alpha and L harmonic, all right? Okay. So this is going to follow from the following. So you just let B1 and B2 be two balls in the domain D such that B1 closure is contained in the ball B2 and B2 closure is contained in the domain D. Okay. Then if we apply the interior Schroeder estimate to the ball, we take the domain to be B2. Okay. So because B2 closure is contained in D, if I take the function un minus um, this is bounded on B2, right? And if I take L of un minus that is going to be 0 again. So the interior Schroeder estimate says the C2 alpha norm of un minus is going to be bounded by a constant times the C0 norm on B2. I'm taking, instead of the whole domain D, I'm taking the ball B2. So the C0 norm on B2 plus this F will be 0. This LU is 0, right? So I'll just get constant times the C0 norm. Okay. So that's what I get. So I get that the C2 alpha norm is on B1 closure on the small ball is bounded by a constant times the C0 norm on the big ball, B2 closure, right? Okay. So this right-hand side goes to 0 as Mn tend to infinity because the UNs are converging uniformly on compacts. In particular, they're converging uniformly on this compact B2 closure, right? So that means that my sequence UN is Cauchy in the space C2 alpha B1 closure. But this is a Banach space. So therefore, it follows that this is convergent in this Banach space. And so therefore, the limit function U is in C2 alpha B1 closure for any ball. Okay. With B1 closure contained in D. Is this clear?
Yes.
So that proves the fact that the limit function is also in C2 alpha. So therefore, it's in C2 alpha of the whole domain. And finally, since L from C2 alpha B1 closure to C alpha B1 closure, this we already saw is a bounded linear map. So therefore, LUN will converge to LU, right? And the LUNs are all 0. So therefore, LU is going to be 0. Is this clear?
Yes, sir.
It's just continuity of L, right? It's just continuity of L. Okay, so that proves this corollary. And I think we have, 4 minutes. It should be enough to give the final, the main theorem, which is a solution to the Dirichlet problem. LU equal to 0 in the ball and U equal to phi on the boundary of the ball, where B is, this is the Dirichlet problem, the homogeneous Dirichlet problem, right? You want an L harmonic function with given boundary values phi, okay? Okay, so let L be elliptic and suppose the coefficients are Holder continuous on the closed ball and C is less than or equal to 0. Then for any phi in C0 of the boundary of the ball, there is a unique U in C2 of the ball intersect C0 of the boundary of the ball such that LU is 0 in the ball and U is phi on the boundary of the ball. Okay. So Let me see. Yeah, I think we can finish this. So the idea is, given phi a continuous function on the boundary of the ball, we can choose a sequence phi k which are smooth on the boundary of the ball, such that phi k converges to phi uniformly on the boundary of the ball. And each phi k, because it's smooth, we can extend to a function phi k in C2 alpha of the closed ball. Then by the previous theorem, we know that for C2 alpha boundary values, we have a function uk, which is in C2 alpha of the closed ball, such that LUK is 0 and UK is phi k on the boundary of the ball. And since this C is less than or equal to 0, by the maximum principle, we have that the sup norm of UK minus UL on the closed ball is less than or equal to the sup of UK minus UL on the boundary. And on the boundary, this is equal to phi k minus phi L sup norm. And this goes to 0 because the phi k's are converging uniformly on the boundary. So that means that UK converges to U uniformly on the closed ball, right? And since the LUKs are all 0 and the UKs are C2 alpha, this means by the previous corollary that U is in C2 alpha, right? And LU is 0, okay? And since they converge uniformly on the closed ball and the UKs are equal to phi k on the boundary and phi k is converging to phi, we get that the limit function U is equal to phi on the boundary. Okay, is this all right?
Yes, sir.
Yeah, so that's it. So yeah, so the approximation argument, all we need is the maximum principle, right? To get convergence on the in the inside, uniform convergence on the whole closed ball. And then we're done by the previous corollary. Okay. Is this all right? Yeah.
Yes, sir.
Okay, so we've solved the Dirichlet problem for a general operator on the unit ball. The only hypothesis are the coefficients are Holder continuous and the zeroth order coefficient is less than or equal to 0. That's it. So if you have more questions, I can do another 5 minutes, otherwise we can stop. So okay, then we stop. Yeah. Okay, so see you Thursday then.